So with all the water that's coming into our house and it gets used, and then once it's been used, it is wastewater. And again, there are a number of ways that it can be dealt with. If you're in a municipality, it is probably a city sewer line. It could also be a combo line where it is stormwater and sewage combined. Sewage is waste that comes from buildings and people that can have biological elements in it, whereas storm drains are specifically for rainwater. If you are not on a public sewer or sewer storm drain line, then you need to have a septic system. And according to the EPA, approximately a quarter of U.S. homes are on septic systems. Your book has quite a bit on septic systems. This is just a little diagram here. And I'm just going to point out there's the size of it is based on the number of bedrooms, not the number of fixtures in the house. And the concept is that there's a septic tank and a drain field. And the system has to be sized. There have to be access points throughout. The septic tank might need to be inspected and or cleaned out every so often. The way that the size of the drain field is set up is based on both the capacity, the number of bedrooms, and a soil test during the wettest part of the year to see how much liquid the earth in that particular place can absorb, so that you're not saturating the ground and not, it's got to sink down. And as it sinks down, it's important to keep in mind that that waste and the biologic elements that are in it get cleaned by microbes and sand and a lot of things. So by the time it gets down to the groundwater, it is completely drinkable water. If a house has a garbage disposal in the kitchen, the whole system needs to be another 50% larger. So if you do have clients, or if you yourself are on a septic tank, keep in mind that instead of using a garbage disposal, if you compost, you are greatly reducing the load that is on your septic tank, which means it's going to perform better and it won't have to get pumped out as often. So along with the waste, which is any water that's been used that drains out of the bottom of our fixtures, along with anything else, food scraps, biologic materials, toothpaste, what have you, that's all going down into a drain pipe that's either leading to our sewer or to our septic system and our drain field. But along with that, we also have our vent pipes. And that vent pipe, there's a main stack, as you see in this diagram. The venting is yellow, and the liquid part of the system is blue. The vent pipes, the main portion that we see to the right of this is called a vent stack. It's also referred to as a soil stack. Plumbers refer to solid waste as Soil, it comes from an older English term of night soil, meaning number 2, to use a childhood determination of the sort of waste that's left in the toilet. So soil stack, vent stack, and that is to get any sewer gases that are created by those biologic elements biodegrading. So methane is something that's created. There's other gases, and those gases are quite flammable, and they also can create pressure in the pipe. And so early on in plumbing history, it was discovered it was a really good idea to run some pipes up through the roof, that it would allow those gases that are lighter than air, certainly lighter than the liquid and solid waste, to rise up and get out. Now, most of these are going to be in our walls, and the vent pipe size for a single fixture is going to be fairly small, 1¼ to 1½ inch diameter. I will point out also that all of the diameters that are mentioned in this lecture for your supply, vent, and waste size are all in your reading as well. So when you're doing your homework, if you need to refer to a size, I really encourage you to look at the PDF reading that you have for this class. Excuse me, it might not be a PDF, it might be a Google Doc. We're a little bit in transition right now. At the exterior, above the roof, it can be a larger size. And last time when we were looking at mechanical ventilation, I showed many pipes coming up through the roof, and the first image that we saw were some plumbing stacks, and those are the vent stacks or soil stacks. So that 2-inch diameter should be something that you remember from that slide. You can also go back and look at it if you want to remind yourself. Notice also that when the vent from the lavatory, shown on the left, is connecting to the main stack, that the horizontal is over 6 inches above the bottom of the lavatory where it drains in, and that is to make sure that gases aren't getting back into our spaces through the waistline. Also, besides venting gases, having that air pressure in there also helps create seals and regulate the waste. The interface with our framing, again, the pipes are fairly small, so they're drilled in joists and wall studs, and they go up through the roof. Up at the top, ideally, they have caps to prevent rain from entering the pipe. However, most plumbing vents that I've noticed do not have a cap on the top. Many materials are allowed. Plastic is extremely common, as is cast iron. It is important, and your plumber should know the regulations about what is allowed for above ground drainage and any vent pipe materials that are allowed underground. They can be different. For our waistline, it's important to keep in mind that gravity is part of how the waste leaves the building, and therefore they must have slope to them. the smaller the diameter of the waistline, the more slope it needs to have. It is a 1/4 inch of slope per foot in a 2.5 inch diameter or less pipe. So if we look at our lavatory there, the line's coming down, there's a little P trap, and that allows there to be a seal of water in there. We have a little horizontal, and that's going to be our smaller diameter. And then after the large sweep L, we have another horizontal, and that is also that smaller diameter. So those are going to be that 1/4 inch per slope, per 1/4 inch per foot slope. When we get to a 3 to 6 inch diameter pipe, the slope can be a little flatter at 1/8 of an inch per foot. And only at the exterior do we get up to an 8 inch diameter pipe or larger, which can go down to a 1/16 inch per foot. Now, it's important to keep this in mind as well, because if you have a large house and you have a waistline that has to travel horizontally a large distance, if you remember that it needs to angle at least 1/8 of an inch per foot, if not a 1/4, sometimes that waistline is going to come down below our floor joists, and so soffits might need to be designed. It's another reason also why the placement of your plumbing fixtures can really influence the cost of the whole plumbing scenario, so that we can spend more money where it matters on having nice tile and energy efficient but attractive plumbing fixtures. The size of the pipe also depends on how many fixtures are draining into it. Some minimums are for a kitchen or bath, it's that 1.5 to 2 inch size. Our toilets are required to have a larger waistline, and you see to the right that toilet has a much larger waistline connecting into the main waistline there, and then that waistline, the same thickness, is going up as the vent through the roof, our main plumbing stack. It used to be a 4 inch diameter, but the code has, because toilets have gotten better and plastic piping is less prone to have things get stuck in it than cast iron was, we can go down to 3 inches, 3 inch diameter for our waistline. But most of the time we design as if that waistline is going to be the 4 inch diameter. And again, if we look at this diagram, we see the waistline going up and the waistline going down. So where it's the vent stack and the waistline is that larger size. And if you have a wall stud that's 3.5 inches, that's not going to accommodate a 4 inch diameter pipe. And that's why that water wall around where your vent stack is going to be, your main waistline, and certainly behind the toilet needs to be designed to be a 6.5 inch, 5.5 inch wood stud, a 2x6 wood stud that literally measures 5.5 inches. People often want to know about venting islands. I mentioned before that we want that horizontal to be above the bottom of the drain in the lavatory or sink, and we want those gases to go up through the roof. However, people like to put sinks into islands. So it is possible, it's a little more complicated, as we see in this image here. The venting needs to be done in this manner, where we have this sort of U-shaped vent happening in there, because typically the vent pipe has to connect above the rim of a sink by 6 inches or greater, as cited in code. And if you see where the bottom of the sink is, where it attaches to the drain, the top of where that U is, right underneath the counter, that's that 6 inches above. And you might also notice there's a clean out on that vent line. So we have waste going down, we have the venting happening, and the vent is going across the floor and then up the wall, possibly draining up with some other vent lines. One of the houses that has been built in Portland that has all of the water that is collected on the roof goes into a cistern that is underneath the house. This house is on a hill, and it's got quite a lot of property, and they needed to think about stormwater as well. It is called the Full Plain House, and there is going to be a link at the end of this video that is something that you might want to watch. It is a little more oriented towards the landscaping, so I would suggest that you don't watch all of it, but stop at 1 minute 14. There's also a PDF from Mitsubishi about the HVAC system. It uses a mini split. So again, this full plain house, all the water is collected on the roof, and then all the waste is dealt with on site. This is a diagram looking through if you don't get a chance to look at the video. As we see, A is the rainwater harvesting. So this roof has 1,273 square feet of metal roof. It is expected to capture 21,400 gallons of water per year. The roof shape is called a butterfly roof. It's inverted, and it's all collected and held in a cistern underneath. That cistern is C. It has a 12,000 gallon capacity. The water is held and treated for potable use. So potable, again, meaning drinkable. B that you see up there is a list of all the fixtures in the house. There is a shower that uses 1.6 gallons per minute, a hand washing lavatory that uses 0.5 gallons per minute, a washer, clothes washer, that uses 15 gallons per use, a dishwasher that uses 1.5 gallons per use. And I will say that even the least efficient Energy Star dishwasher only uses 4 gallons of water to run the dishwasher. And that's one of the reasons why people who are interested in saving water believe that dishwashers are actually more efficient than hand washing the way most Americans hand wash. Which gets me to also the kitchen sink at being 1.5 gallons per minute. So just to backtrack for a second, if you're running the kitchen sink for a full minute, that's 1.5 gallons. And if you're running the whole dishwasher load, it's 1.5 gallons. Now, of course, there's electricity as part of that, but that isn't part of the water saving. The estimated usage is less than 50 gallons per person per day in the cool season and less than 65 gallons per person per day in the warm season. So that 12,000 gallon capacity cistern is going to work out just fine. E is showing a cistern overflow. So if more water, if we're getting 21,000 gallons of water over that, but our cistern only holds 12,000. If we're not using enough water, there is an overflow. It's underground quite a bit, and there are some soakage trenches that are perpendicular to the view that we're seeing here that allow the water to infiltrate into the surrounding soil. Then all of our waste lines are going into a gray water system, which is D. Toilets, as you know, are not gray water, and that's why toilets aren't listed on here. They actually have a composting toilet, so the toilet doesn't use water at all. And all of the water that comes from the items that are listed, the shower, the washer, the dishwasher, the kitchen sink, and the hand washing sink are all approved for gray water. Now that is going to be coming down slightly underground and hitting the fruit tree zone, which is about halfway down the property. There's also, as I mentioned, water, storm water that can be coming down from across the street, as this is a hill, which is that overland flow, and anything that is falling from the sky and not hitting the roof. And that's designed to move down the hilltop. If there's enough that it's not just soaking in, there are some infiltration basins that are swales that are designed to hold it, and some terraces along the way.